Today we're going to look deeper into Bohr's model of the electron shell model that we looked at previously in topic 7. We're going to conceptualize electrons and electron energy levels as standing waves. We're going to express angular momentum and introduce angular momentum for that matter, and express it in terms of these orbital or energy levels. And we'll be talking about something called a quantum number and relating that to these energy levels. First, in review, emission and absorption spectra illustrate this relationship between a photon and an energy level. Emission spectra is when specific photons are given off, depending on the arrangement of the electron energy levels. And absorption spectra is when an entire spectrum is emitted, withholding specific frequencies which relate to specific energy levels within the medium. Now, at these specific frequencies, what we're getting is a change in energy level of the electron. The electron is either emitting, it's either going down at energy level and emitting a photon, or it's absorbing a photon and going up an energy level. This was all postulated by Bohr, who tried to remove this idea of an electron orbital as a satellite orbiting the nucleus, and came up with this idea of specific energy levels which relate to some kind of exchange. And then experimental data demonstrated that this was in fact true. Now, in the previous lesson, de Broglie postulated this idea that electrons were actually waves. And from Bohr's idea that electrons are existing in these energy levels as particles, the next step would be then to formulate some kind of model which interprets these electron levels as waves, right? So if an electron is a wave and electrons live in shells outside of the nucleus, how do these shells look like if they're waves? So that's what we're going to do now. How do we conceptualize electron energy levels as waves? And Schrödinger got involved in this and came up with the following. Now, first, though, we need to take a step back and define something called a standing wave. Now, if we go back to topic 4, we define something called a progressive wave. A progressive wave is simply a wave that has a source and travels through the medium. So we've got an example here. And you can see quite clearly it has an amplitude, it has a wavelength, and it's traveling. And it starts like this. You have an initial wave at its source, and it moves, and then what you can see is that the crests travel along, okay, and change. And we have a change there in amplitude, but also in position along the x-axis, right? Everything's moving along this way. Now, that's what we call a progressive wave. But there's also another phenomena called a standing wave, which you can see here. In water, what we're seeing is that we're still getting this motion, this change in amplitude, but the wave doesn't seem to be moving along the x-axis very much, right? And here you can see not at all, right? And here you can see these really clear ideas of standing waves. So a standing wave is simply a wave that doesn't seem to be going anywhere. It is in fact a bit of an illusion. Stop this video and have a watch of this demonstration where we can see set up on this apparatus a standing wave. Okay, you'll be able to see what it looks like. Welcome back. So now you know what a standing wave looks like. You'll be able to understand how a standing wave is produced when you have a progressive wave, a wave that moves along and reflects. And if you get that frequency just right, then you end up with this very specific situation where the wave looks like it's standing still almost. It's not, in fact, standing still. This is a consequence of something that's called interference and superposition, which we introduced last year. Don't worry about that too much because, as I said, we will talk about this in topic 4. But the important point here is that a standing wave has the main properties of a progressive wave. It still has a wavelength which corresponds to a crest and a trough, right? So that would be one wavelength. The amplitude, or the maximum displacement, still corresponds to the amplitude. And there's another level of understanding that we can apply to it. There are three types of standing wave. We're only going to consider one type right now, and that's a standing wave that's set up in a situation where it's fixed at both ends. That means it starts here at 0 displacement and ends here at 0 displacement. So let's have a look at the properties of this type of wave more closely. Now, depending on the frequency of the standing wave, your standing wave could look like this, so it has only one peak, right? Or it could look like this if the frequency was a little bit higher. Or you could increase the frequency and make it look like this, and increase the frequency and make it look like this, and so on. Now, the way that we describe the difference between these four situations is using a number called a harmonic. A harmonic depends on the kind of level of complexity of the standing wave. Here, the harmonic is 1. We can see there's one peak, and it's in its simplest form. This also happens at something called the fundamental frequency. Again, that's not important for now, but this number is. As you increase the complexity, you increase the number of the harmonic. So you can see here, this is the second harmonic. You've got 2 peaks, and this is your third harmonic and your fourth harmonic. But the important thing is that the n number, which we're going to look at in a moment, goes up depending on the complexity of the wave. So you need to be able to recognize the n number from a picture of the wave. So make sure that you understand the connection between the two. So now I'm going to introduce one of the key players in quantum mechanics. It was Erwin Schrödinger. Now, he came up with something called the electron in a box model. So his idea was that the electron energy levels corresponded to standing waves on each level. And so that then enables you to calculate the de Broglie wavelengths of an electron based on length L. Now, what do we mean by length L? Now, for that we need to formulate an equation defining these standing waves. So let's look at this standing wave a little bit more closely. We can see that a standing wave of length L, right, if it has, specifically in the first harmonic, looks like this. Now, the general equation for this standing wave is the wavelength of this wave would be equal to twice the length divided by the number of harmonic. Okay, and you can see that applies here, that the wavelength would be equal to 2L, so it would be this distance times 2 divided by 1, right? Now that's a general equation. If we look at the second harmonic, N2, lambda, the wavelength of this standing wave, would be equal to twice the length, this length, plus this length, divided by n equals 2, right? So it would give us this wavelength, it would be half, etc. So the important thing is that you understand this wavelength, this equation and how it works. If you haven't come across before, don't worry, because we will go back to it. But you just need to understand this now. Okay. Now, if we go on to conceptualizing the atom using this idea, it would look something like this. This is what our energy levels would look like. Okay, so our first level, n equals 1, would have this. This would be our energy level now. Okay, so level 1 would have a standing wave with 2 peaks. Okay, it's confusing because this n corresponds to an energy level. Harmonic, in terms of harmonics, this would be the second harmonic. So we've got two different n's. It's not my fault, that's physics 4. So we have to be very careful about this. Here we have our second level, right? And it corresponds to 4 peaks. So this would be our 4th harmonic. And then this is our 3rd energy level, which has 6 peaks. And that would be our 6th harmonic. Does that make sense? So let's have a look at the maths there, right? So if we have a circumference which contains complete numbers of wavelengths for an electron wave, right? Then let's think about a circumference. 2 pi r is an entire circle, right, which is our energy levels, equals n lambda, number of wavelengths. How many complete wavelengths do we have? Oh my god, it's another n. All right, let's see if we can keep it together. We know from the de Broglie equation that lambda is Planck's constant over the momentum, right? Got that? Now, if we rearrange, 2 pi r equals the number of complete wavelengths, n, times h, Planck's constant, over momentum. So this gives us a general equation which looks like this. Now I'm going to introduce a completely new quantity now, and this is a little bit absurd because it's not in the syllabus at all, and I'm going to throw it in now. It's called angular momentum. Angular momentum is like momentum for things moving in a circle, right? It's the vector product of the momentum, which is a vector, times the radius. Okay, you don't come across it anywhere else in the syllabus, and you don't really need to do much with it. You just need to know that it exists, and it's equal to mvr. Okay, this is called angular momentum, and what we've got here is a proof that the angular momentum of an electron in a shell is equal to the number of wavelengths times Planck's constant divided by 2 pi. Now the angular momentum of an electron is then fixed. It's quantized, that means it's a fixed amount, in integral values of Planck's constant over 2 pi, right? Where n is the quantum number. So now I'm going to give you a completely new definition for n. I know it's really confusing. N is now called the quantum number, or the orbital number. It equates to the orbital number, and it also equates to the number of full wavelengths. Does that make sense? I hope so. If you are a little bit lost, the important thing is, can you use this equation? Do you understand that this is mass, velocity, radius of the circle? N is the number of full wavelengths on your standing wave, or quantum number, or orbital number. This will get easier when you actually look at some questions. And then you've got Planck's constant, and we've got 2 pi. Apply the formula, you should be fine. Just as a reminder, the rotational equivalent of linear momentum is angular momentum. We'll say no more about it. Okay, so I think that's pretty much it. This video basically explains what I'm saying, but in a slightly different way. So you might be better off listening to that if you're still a little bit lost in the forest of ends and everything else. And I'll come back to this at some other time. So I think that's that for today. Apply this equation using these questions, or the assignment that's on, which has got some slightly easier questions first, and then you'd be able to do something like this. Good luck.